Hello. Today I want to cover an introduction to machine learning methods for image and video analysis. The methods we're going to cover are pretty general and they extend way beyond image and video analysis, but our eventual focus will be on image and video analytics. Okay. So I want to start by the motivation. Why do we want to study such problems? Why do we want to apply machine learning? Then we will look at the metrics, specifically the receiver operating characteristic curves. And we will look at a specific problem, the content-based image retrieval. We will look at precision and recall and how it relates to that. The third topic is how do you set up the basic training and testing, okay? And then we will look at cross-validation, a very simple introduction to statistical learning theory, and how do you do training for deep learning methods. Let me begin by motivation. Here I have a study by one of my students. He looked at, in his PhD dissertation, the summer of 2019, he tried to develop a model that predicts what a cardiologist will see. So in this example, you can see that the results, that is accuracy for the first cardiologist, and then we have the second cardiologist, and against that we have the machine, right? So you can see the performance of a cardiologist for this problem. So in this case, he's looking at what we call a 1-year mortality prediction. In other words, you examine the data and you predict within 1 year if the patient is going to survive or not. Okay, and we're looking at he's looking at a data set of 600 samples and what is called balanced prevalence. So he has a balanced data set, 50% of each type, people who survived and who did not, and that's a classic. We want our classification databases that we use for training and testing to be balanced. We want to have equal number of normal versus abnormal, equal number of disease versus non-disease. And by doing so, we don't specifically bias towards one group or the other. Okay, so on the left plots, we have the accuracy overall, but then on the right-hand side, we have a graph that we will study, which is basically what we call sensitivity versus 1 minus specificity. We shall cover it later, explaining much more. But for right now, to understand what is happening, it suffices to say that this line over here is the worst case scenario. In other words, a straight line from the point 0, 0, right here, to 1, 1, represents random sampling. In other words, we randomly, a random predictor. In other words, a predictor which assigns with 50% probability, simply the patient goes in and with 50%, we assign them normal or abnormal classification. Or in this case, 50% chance they will survive after 1 year, 50% chance they will not survive after a year, right? And what we want to do, again, is we study in this what we call the ROC curve. Let me just make this smaller, is develop systems that stay above this curve, right? So in this example, in his dissertation, he generated the graph that is shown here, right? And this is the graph that corresponds not just a single classifier, but actually what we call a family of classifiers. In other words, on one end we have one extreme, and the other end we have one extreme. In one case, we're not going to cover this until later, which was which. We have a predictor that simply sends everybody home and says there is no problem, there's no need, everything will be normal, right? And then the other one, on the other extreme, we have another predictor that basically says, well, we predict that the patient is not going to survive within a year, and therefore we should do more testing, okay? And between those two extremes, we want something that is actually more sophisticated, right? It sends people home when with high probability they're going to be normal, and it keeps them and recommends a treatment to avoid, to have them survive beyond a year. We have treatment if we predict that they're not going to survive based on the current data. So again, the therapy here depends on a prediction within a year. Anyway, so it's important to understand that this is a family of classifiers, right? So this is a collection of points that generates a graph, right? So, and there is going to be a threshold that we need to study carefully of how to move along the graph, right? Based on how sensitive you are to this classifier. And once you design a classifier and you set all the thresholds, you generate points. In this graph, this is the machine acting as a single point after we set up all its values, and then we have the two cardiologists acting right here. Is two dots on this graph. Okay, so another thing to notice that again, we're going to study this much more extensively, and right now we're just literally trying to understand where the graph is that at this point up here, this is where we are going to want to be. And again, we're going to try to understand this as it comes up, but essentially this is the point of specificity equals 1 and sensitivity equals 1, okay? So in the graph is shown as the x-axis will be at 0 and 1.0. So if you are here, you're basically, this is what we call the ground truth. At this point right here, you get everything correct all the time. Right? When you say somebody needs to go home, that means they will definitely survive beyond a year. When you put someone through additional testing, with a 100% probability, you're right. So if you're at that point, now I'm going to switch to the left to this graph here. If you're at that point, then we have 100% accuracy. Okay, that is we will be able to tell with 100% accuracy without ever making a mistake when somebody will survive or not. And so in his study, he has you can see that the overall accuracy, even though the arrows is a far better metric here on the right, you can see that the overall accuracy of the machine is higher for this problem than the cardiologist, right? You can see that the machine achieves a result that is, if you go back to your graph, is around here, which is higher than any of the individual cardiologists. And then the little p-values here, it's a little test that basically establishes that the lower the value, with 0 being the ideal, means that that's the probability that the differences are significant or not. In other words, if this value is very close to 0, then there is truly significant difference between those two classifiers. This is, in other words, the performance of the machine with such low values, threshold is usually set around 5%. It shows that the machine not only is it doing better, but it's also doing substantially better. It's not just due to random chance, right? And you can see, though, on the other hand, right here, there are significant differences between those the two cardiologists. However, there is much bigger difference between each one of them and the machine. Okay, so again, you want this p-value, and these are the concepts we need to understand. Okay, we need to understand whether a patient will survive or not. Now, in addition to all of this, we have a concept for each point. Notice that he plots, let me clean it up a little bit. He has another, he goes back to the graph, right? And basically identifies for each person the sensitivity and specificity. So all he's doing is that he projects to the y and the x-axis, okay? And based on the y and the x-axis, he generates the sensitivity and specificity. Okay, and what's important here is that the best one will have 100% accuracy on both, right? So you whether whereas the 100% sensitivity, 100% sensitivity, and specificity, and again, we shall see that later. Notice that the cardiologics are a little bit unbalanced, right? You can see that they are basically they have higher specificity than sensitivity. In other words, they do not, roughly speaking, what is happening in this example is that there is a wide gap between what they're telling and what is actually happening here. Whereas in the machine, in this example, it's far more balanced, right? You get pretty much the same accuracy of sensitivity, specificity, and as we shall see later, this wide gap comes from a natural human tendency to be positive, right? If you're more positive than you are negative, then what's going to happen is that you'll tell people that they're 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 most likely to do well versus not in this example. Okay, all right. Now, in order for the student to generate this, he used a pretty large data set. Okay, so in this example, he used actually 723,754 videos, and it's a huge data set from 27,000 unique patients. So many times these patients were basically coming back because they were being monitored. And the results that we presented on 600 samples are actually the test set. So again, this is the final results on what we call a test set, right? Which is an independent set, which is different from the original training set. Okay, so this is training, and this is tested. Okay, all right. So then the big question is, how do you develop systems that balance all of this and generate all these different thresholds in this motivating example? Okay, as you can see, if you can achieve if a machine can be designed that it can really help and perform as well, we were very interested in developing it. Okay, so the big concept here that we need to study in more detail is understand the graph on the right-hand side. In other words, truly understand what we mean by a receiver operating characteristic.